It was rare when Elvis would do a movie song live in concert, but you're about to hear more of the king of rock and roll live doing his great movie songs.
Yeah.
Stuff from his last film.
I'm driving out to the desert. I found a great location for my astrophotography experiment not too far from Las Vegas. This valley has pretty dark skies, and I believe it's an ideal location.
When I come out here tonight, such a nice, wide open space. And, yeah. Love the desert. Astrophotography in the desert is unbeatable, man. Unbeatable. There's that mountain.
Triangulation is a simple concept, yet it has limitations that need to be understood. Triangulation can be carried out with any direction-finding equipment like antennas. In our case here, we'll be using optical instruments, namely a camera, or two cameras to be exact. And as you can see in the graphic, there's some uncertainty due to the measuring equipment. And that uncertainty translates into an error ellipse in the location of the target. And the farther out that we push the instrument, the larger the error ellipse. And for our camera and the lens that I'll be using, the 50mm focal length, and given the pixel pitch of the sensor, I have an uncertainty of about 0.0000784 radians. And that translates to a range of 12,755 miles to infinity. So the instrument is useless beyond that, you know. And so you may be wondering, like, why would I even be trying something like this, you know? But just out of curiosity, I said, I'm going to try it, see what happens. And I'm also hoping that by integrating and taking multiple images, I can reduce and average the data to get better resolution, sub-pixel resolution. Now, once we determine the angle A, okay, then we can use the equation we see there. And when we're going for things in the distance, for small angles, it is just d over a. D is the baseline. So I'm pretty excited. At night I carried out the experiment. The skies were clear and the moon was just a sliver, emanating just enough light to highlight the mountains on the horizon. Perfect conditions.
So I'm recording at night. Here's one of my cameras. And there's my car. Oh, starry night. And the other one is about a mile down there. And I didn't see any signs over here, but I looked at my my odometer. So I'm doing 30 exposures. I missed a few because I had to drive over here. But I'm looking at the mountain. Oh, this is gonna be good, man. This is going to be good. Whoa, there's my timer right there. It's hanging. It's gonna be good. It's gonna be good. See, it's right there. It's my timer. I have two identical ones. I didn't get the camera quite level. It's all messed up. I hate this stand. It's so annoying. But anyway, I got a tower there to align. This is gonna be good. Okay, so mile marker 6. There's my camera right there. See, mile marker 6. Whoa, turned off.
So my second
My
camera on
camera's
the
turned off.
right was left unattended, and I actually flipped up the screen so people would not see this light and maybe stop and take my camera. But there is my camera right there, and I started both of those at this location, okay, and then put the other camera in my car and drove up the road about a mile, just looking at the odometer, and set up real quick. So I missed a few frames in the process. So here's the diagram of my experiment. So I used two cameras separated by 1.177 miles. I had to actually go back and drive and get the distance more accurate. And I use my laser rangefinder as well. But this is to scale on the map exact distances. Okay, so we will determine the angle A. And after we have the angle A, then we can correct the images and align the cameras so they're parallel. Okay, and once they're parallel, then we can get the angles to different stars out there and do the calculations. So, but there's more work. We also have to think about elevation. And notice at the top there on the left, we have to correct for the baseline. There's a 15-degree angle between the road, the Tecopa Road, and the direction towards the tower. And I actually aligned on the tower. So I'll show you some images now of how I extract the data. So I chose this mountain, Mount Potassi, because there is an antenna tower on top, and it has this red light beacons, and I'll tell you later why that's very important. And so I bring in two images from the two cameras, and then I copy one onto the other, and I turn the transparency to about 50, and then I shift them and align them. All right, so as you can see here, we can get that looks pretty good. Maybe in between this position and the other one. Actually, this one looks pretty good. So just visually, I align the two images, and then I begin to measure the distance between the stars as seen by the two cameras. And here it's very tricky. There's not a whole lot of stars, but when they overlap, it's hard. So there's 3 in a triangle. So I actually enable visibility, and I kind of memorize. So there's nothing there. Boom, there they are, 1, 2, 3. And so then I just start measuring the distance between the two. And here I notice my screen grab is not showing the dimensions on the bottom, but it's about 849 pixels. So lots of stars, lots of data. So I took 30 frames, but I lost like about 7 for one of the cameras as I was driving to the other location. So I only have about 22 useful ones. But I measured about 8 stars. And so, let's say 10. If I do 10 times 20, I'll have like 200 data points. But I actually just analyzed about 70 or so, and I realized the statistics are actually pretty good, as you'll see. It will blow your mind. Yes, my friends, I have done it. Before we look at the data, here's the map. So we're going to zoom in and look at the towers as well. It's very critical that we get the dimensions accurate. So there's the tower FM station up there, and here we're going out to mile marker 6. That was the camera on the right, and we will have a look in street view. Let's see. There it is, right there. Yep, mile marker 6. So now the other location did not have a plaque, and so I ended up driving the next day, going back and forth. I used my laser rangefinder, and I got the distance to what was it, 0.01 of a mile. So here's Mount Potassi, here's the station. Where is it? There we go. And let's look at the photos available. Here's the tower. You can see the shadow on the ground. Let's go up here. Yep, there we go. So there's the tower. And yeah, it has the lights on it, and that enabled us to align the images. So pretty cool. And I'm out there, somewhere out there. I'm heading back out because I need to get that baseline perfectly, and I'm gonna go look for the spot where the left camera was at. A beautiful day again, just lovely.
Love that desert. Here's all the construction that I saw last night. So I was at mile marker, let me turn this down. I was at mile marker 6, and here's mile marker 8, and it's 7, let me see, it's 15350, okay. So 0.1. So I'm gonna see if I can find the spot where I was at. So this is a good spot. Very easy to identify. Wow, look at the view of the mountain. Whoa. So beautiful. Mile marker 6, and there's the mountain. All right, so now I'm gonna reset this thing. How do I reset it? Okay, I reset the trip meter. So now we're gonna go to about a mile, and I put some rocks out there. We'll find them. The desert looks pretty cool. Point 3. 0.4 or a 0.4, 0.5. It's the mountain. Woo! But man, these bushes. 0.5. 0.6. Let's see. There was a tall bush, and then there was some stubby desert palms, or whatever these things are called. This little palm-looking things. 0.8. 0.8. Oh, is that it? No, that's not it. 0.8. 0.9. 0.9. 1 mile. I think I went a little bit beyond the mile because I couldn't see the pole. Oh, this could be it. Oh yeah, I see. I think this is it. Yeah, I found it. I can see the tire marks. Yeah, this is it. Woo, we found it. All right, we found it. This is exciting. All right, we found it. So here it is. I put this rock inside of this thing right here, right there, and those. So yeah, I had the tripod out here, and now I brought my. Okay, let's see. I brought my laser. Let's see. Can I see that thing from here?
Unfortunately, the laser rangefinder did not work at that distance. And what I ended up doing is driving from mile marker 6 until my odometer exactly changed to 1.2 miles. And then I used my laser rangefinder and look back at this location where the camera was, and I realized it was 40 meters, so around 120 feet or so, and that's how I got the 1.177 mile baseline. So yeah, we needed accuracy, and I got it. So here's the graphic to illustrate why everything is important. So the baseline along the Copa Road is 1.177 miles, okay? And there's a 15-degree change there in the direction of the towers, okay? So we adjust for that and we get 1.137 mile baseline, okay, towards the tower. So that's very important. All the small adjustments are important. Then the distance, as seen from the top, is 17.32 miles, the yellow triangle on the ground, to the right side camera, okay? Then the difference in elevation is about 5,300. Notice that there's a slight elevation between left camera and right camera. So average is like 3,150. Okay, the tower is 8455. Yeah, so it's about 5,300 feet. And we use that with 70.32 miles to get the 3.32 degree difference. Okay, so we can get the slant range to the tower of 17.04 miles. Now, since this angle is so small, the angle alpha or A, which is 0.066725, the difference between an arc segment and the chord is actually very small. So the D over A approximation will hold. Now this angle alpha or A, when divided by the angular resolution of 1 pixel, which is 0.0000784, produces an incredible 851.1 pixels, 851.1. Well, when I was measuring the stars, I was getting around 847, 48, sometimes 49, sometimes 46, and it just blew me away. I said, whoa, that is incredible. Anyway, this angle alpha is the angle that if we shift the image by that amount, then the two cameras are calibrated and exactly perpendicular. But we don't really have to do that. We just take the difference between the distance of the stars, that we measure, and 851.1, and that gives us the difference in angle from the stars to the antenna. And what I found out just blew me away, folks. Have a look at this. I plotted all my data in a histogram and found the average 847.63 pixels, standard deviation, and the confidence interval, and plugged that into my equations, and I was blown away. The celestial dome distance is 4,200 miles away. Just incredible, folks. Within a 95% confidence, we can say that the distance is between 3,800 and 4,600 or so. Just incredible, folks. And this was only 9 images. I still have more. And if I analyze it more and gather more data, I'm only going to tighten that confidence interval. This is incredible, folks. What does this mean? We saw that the sun, in my previous analysis, came out to about the same distance. Yes, my friends, things are very mysterious out there. Yeah, I have done it, folks. Anybody that wants the data, I can give it to you, and the images. This is truth, folks. Some people think I'm trolling you. I smile and laugh at times, but I'm serious about science, and there is an explanation for this, and it's refraction. Light from distant stars diverges as it enters and approaches the surface. It's a divergent phenomena which produces virtual images. So the stars are not really there. The calculations we've done in this graphic are along the light blue lines, right? So the red is the light comes and diverges out, and we measure its angle on the surface, and the calculations assume straight line propagation. Therefore, they intersect at a distance of about 4,200. But it's really the curvature of light that does that. And this indicates that higher up, light travels slower than down below. So it's really incredible. Or, as the flat earth community believes, there is a dome. The holographic dome. We'll talk about this in the future. I encourage you guys to subscribe. I have a lot of interesting topics I want to cover. Satellites, I started a series. I've been everywhere, as you probably know by now. And I will share with you what I know. And so thank you very much for following along. But before we go, I wanted to find something out about Mount Potassi. I said, what's the meaning? I gotta throw something cultural in this presentation. So I pulled up Wikipedia, Potassi Mountain. Potassi Mountain is about 30 miles southwest of Las Vegas in the Spring Mountains of Clark County, etc. Okay, limestone bedrock. History, the giant cave at Potassi Mountain was used by Vision Quest by Shemehuvi etc., Spanish missionary. And then as I was reading down, notice at the bottom it says Potosi Mountain was the site of the TWA Flight 3 air crash that killed 22 passengers, notably the actress Carol Lombard on February 16, 1942. Oh my God, that's like 80 years ago. Wow. And 2 months ago. So I pulled it up. There's Carol Lombard, was an American actress, particularly noted for her energetic, often offbeat roles in screwball comedies. In 1999, an American Film Institute ranked Lombard 23rd on its list of the greatest female stars of classic Hollywood cinema. Whoa. Yeah, maybe your grandparents were, looking at movies from that era. But I was curious, like, what in the world happened? Here's a short clip of Lombard.
If you had it all to do over again, would you have married me?
Okay, so let's see what happened. TWA Flight 3, twin engine, Douglas DC-3, blah, 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 operated. Okay. Was on a scheduled domestic passenger flight from New York to Burbank, California, in the United States via several stopovers, including Las Vegas, Nevada. On January 16th, 1942, at 19:20 Pacific Standard Time, 15 minutes after takeoff from Las Vegas Airport, now Nellis Air Force Base, bound for Burbank, the aircraft was destroyed when it crashed into a sheer cliff on Potosi Mountain, 32 miles southwest of the airport at an elevation of 7,770 feet above sea level. All 22 people on board, including movie star Carol Lombard, her mother, and 3 crew members died in the crash. The Civil Aeronautics Board investigated the accident and determined that the cause was a navigation error by the captain. Oh my God, that is terrible. Jeez. Yep. So there is history there. I wanted to get the meaning of the mountain, and I didn't know about this. I found some pictures online. The wrecked engine, I guess, is still up there. So I may go for a hike up there. I'm curious. And I'll certainly be watching some classic movies with Miss Lombard, so I can, get a little bit more educated. Now, here's a diagram from the investigation. Yeah, so this is a diagram for the investigation. I was reading online a little bit. It looks like they were flying along a compass direction, and that was wrong. It's similar to Boulder City. Those guys were used to flying from Boulder City, but they landed at Nellis, and the investigators thought that was wrong. You should go along, I guess, a radial of 205 there. So anyway, there was a few things that contributed. It was wartime. Some of the beacons were off except one of them. And it's like, oh my God, moonless night. Couldn't see much in the dark. And wham! When you run into a mountain like that, geez, you don't even know what hit you. It's so sudden, And I guess that's how Mr. Fawcett died as well in the Mammoth Mountains in California. Stephen Fawcett, the adventurer, slammed into a mountain. Yep. Terrible, terrible, terrible. Anyway, folks, thanks for watching. Stay tuned for more in the future. God bless all of you out there. And what crazy times we live in. Pray for peace, folks. Pray for peace. God bless you.